So this is a Born-Haber cycle question. When you're doing the stages on the diagram, what most of you are forgetting were the electrons, so just make sure that the charge is balanced when you're writing them out. So the first step, or the first thing to think about, is that you've got to make sure that you're getting to the two ions in a gaseous form. So if you look at what you're starting with, you're starting with solid sodium and you're starting with molecular fluorine. So we've got to turn both of those into gaseous atoms before we can then turn them into the ions. So the first step you could write as the sodium turn into sodium gas, and then you only change one thing at a time, so the fluorine will stay the same, and then you've then got to atomize the fluorine, which would turn into that. So there's no ionization stages in this question, but notice that then you ionize the sodium, and that creates an electron as well, and then that electron's added to the fluorine to create fluoride ions. That's the electron affinity. So then we are given a table of data, so we can put those onto our Born-Haber cycle to make things easier to then work out the final answer. So that top one, we've got sodium solid go to sodium gas. So that's the first one that we wrote out. So that's plus 109. Then we've got sodium gas going to sodium with its positive charge. That is your top one. And then you got fluorine going to 2F. Now notice we had half of F2 going to 1F. So that needs to be divided by 2 in this Born-Haber cycle, and it's likely that they will put something in like that just to try and catch you out. Then you've got the electron affinity of fluorine, so you've got minus 348, and then you've got the formation enthalpy of the sodium fluoride, which is minus 569. So you're trying to work out this value here in the question. And what you've got to remember is that if you start at this point and go round a cycle and end at that point at the end, then if you add all these together, they should add up to 0. So if we're going to work out this, this value here, x, we're going to do 0 equals, and then we've got to make sure the arrows go in the right direction. So this arrow here, the formation of the arrow, needs to turn around so it's going in the right direction and go back down again. So this one will turn around and that will turn to positive 569. So it's going to be 569 plus 109 plus 158 divided by 2, which is 79, plus 494, so we're out of space, minus 348, and then we've got x, so we could put plus x at the end. And then we need to take everything onto the other side, so x will equal minus 569, minus 109, minus 79, minus 494, plus 348, which gives us minus 903. Now it's worthwhile just checking that your sign matches the direction of the arrow. So we're trying to work out the lattice formation enthalpy with the arrow going down. If the arrow's going down, it's going to be a negative enthalpy change, and that's what we've got here, so that's likely to be correct. So it's minus 903 for the answer there. And then it says, calculate the volume in centimetres cubed of fluorine gas at 298 Kelvin and 100 kilopascals required to produce 1 gram of sodium fluoride by reaction with an excess of sodium. So immediately you should work out that this is an ideal gas equation question. So when we have an ideal gas equation question, I want you to get in the habit of first writing out the ideal gas equation and then writing out the letters of it so we can write the numbers that we're going to put into our equation next to them. So we've been given a pressure, 100 kilopascals, but that needs to be converted into pascals. We've got we're working out the volume in centimetres cubed, so that is x that we're trying to work out. N, we need to work out number of moles. Now the equation that this is referring to, so we are reacting fluorine gas with sodium to make sodium fluoride, which is this one here. So we can work out number of moles of the sodium fluoride, and therefore work out moles of fluorine that would be needed. So moles of the sodium fluoride equals 1 divided by the MR of sodium fluoride, which is 42, and that will equal 2.38 times 10 to the minus 2. So therefore the moles of the F2 required will equal that, 2.38 times 10 to the minus 2, divided by 2, because the ratio of the sodium fluoride to the fluorine is 2 to 1. So therefore that is going to be 1.19 times 10 to the minus 2. So that's the number of moles we need to put in, 1.19 times 10 to the minus 2. That's the number of moles we have to put in. Then our gas constant we have got, and our temperature is 298 Kelvin. That's in the right unit already, so we don't need to do anything with that. So rearrange this to get volume by itself. So V is going to equal nRT over P, which equals 1.19 times 10 to the minus 2 times by 8.31 times by the temperature, 298, divided by the pressure in pascals, and that gives us 2.95 times 10 to the minus 4. Now remember, that gives us it in meters cubed for our volume, and the question has asked it in centimeters cubed, so we need to times that by a million in order to get the answer, and that'll turn it into 295 centimeters cubed if you multiply that number by a million.